I now call upon Ms. Lavanya Ishwar to introduce our speaker.
Good afternoon, one and all. This session, we will have a lecture on Kuttaka Indeterminate Equations of Degree 1 by Dr. Sita Sundar. Dr. Sita Sundar is presently the Secretary of the Kuppaswamy Shastri Research Institute. She is also the Secretary of the Samskrita Academy Madras and Honorary Member of the PS Educational Society, Chennai. She holds an MA in Sanskrit from the Karnataka University, Dharwad, and PhD in Sanskrit from the University of Madras. Her PhD thesis was a critical study on the Bija Pallava of Krishna Daivagnya, algebra in 16th century India. She has participated and presented in papers in various national and international seminars in India and abroad. To name a few, Asthana Kolakalam, an ancient mathematical treatise in Tamil, International Conference on History and Development of Mathematics, IIT Mumbai in 2015. The use of algebra, Bija Ganita, to solve diurnal problems by the Indian astronomer Bhaskaracharya II. 25th International Congress of History and Science, July at Rio de Janeiro. She has also conducted the National Conference on History of Mathematics as Secretary of the Samskrita Academy Madras in collaboration with Sri Chandrasekharendra Saraswati Vishwa Mahavidyalaya, Enathur, Kanchipuram for the Society of History of Indian Mathematics with the sponsorship from the National Mission for Manuscripts, Government of India in the year 2018. She has 2 books published to her credit. One is her PhD thesis, Bija Pallava of Krishna Daivagnya, published by the Kuppaswamy Shastri Research Institute in 2012, and the History of Ancient Indian Algebra, published by the Kuppaswamy Shastri Research Institute in 2023 as a part of the 75th anniversary celebrations of our institute. She has contributed many articles and reviewed many articles and books in various reputed journals. She has also delivered many lectures on Indian mathematics in various schools and colleges. We now request you, ma'am, to kindly deliver your lecture. Thank you.
Namaste to one and all. After some easy arithmetic by Dr. Rama Kalyani, we are going to some interesting algebra. The Kuttaka linear equation of the first degree. In Europe, it was called the Diophantine equation after Diophantus. The earliest Indian algebraists to give a treatment of the indeterminate equation of the first degree of the type Ax plus C equal to By is Aryabhatta. Aryabhatta belongs to 6th century. This was followed by Brahmagupta, Sripati, Aryabhatta II, Bhaskara II, Narayana Pandita, and later Kerala mathematicians like Nilakanta Somayaji, Jeshtadeva and others. We shall be dealing here with the treatment of Kuttaka and Bijaganita of Bhaskara II and Yukti Bhasha of Jeshtadeva. Bhaskara II, the commentator Krishna Daivagnya, has also contributed a lot for the Kuttaka analysis, so we will be quoting him also. The word Kuttaka is a little difficult word to pronounce, derived from the word kut in Sanskrit, to grind. Hence pulverizer. Kuttayati means grinds. Not only is the equation called Kuttaka, but also the method to solve the equation is called Kuttaka by Bhaskara and others. In the equation A plus C equal to By, A is called the Bhajya or the dividend. B is the Hara or divisor, and C is the Kshepa or additive or the constant term. More familiar with that word, constant term. Now, how do you deal with the equation? First, the quantities A, B and C, the coefficients of x, y and the Kshepa, should be divided by their HCF if any, and made what is called Drida. That is, hereafter no more of dealing with HCF. In that state you stop it. That is called Drida. The equation given by Bhaskara is the following. 221x plus 65 equal to 195y. Now we find that by successive division 13 is the HCF. So divide all the three quantities by 13 and you get the equation 17x plus 5 equal to 15y. Now you have to do successive division. So you get two quotients 1 and 7. You do the successive division until the 1 is a remainder. Till then you have to keep doing it. So you get two quotients, or you have to form what is now called a Valli or a creeper. So 1, 7, 2 quotients. Then this is the Kshepa or the constant term. You add that here and then below that you add a 0. Now 7 into 5 plus 0 equals 35. 1 into 35 plus 5 equal to 40. These are the two solutions that you get. That is, x is equal to 35 and y is equal to 40. Now 7 into 5 plus 0, I have showed the method. Now x is also equal to 35 minus within bracket 15 into 2. And similarly you can reduce y to 40 minus 17 into 2. So you get the two equal solutions 5 and 6. So you can write it in general way. X is equal to 15t plus 5 and y is equal to 17t plus 6. So now t can take any values from 0, plus or minus 1, plus or minus 2 and so on up to infinity. Obviously a linear equation represents a line, and of course you have infinite points on the line. That is how you get so many solutions for it. Of course 5 and 6 are the least positive solutions, not the least solution, because you can have negative solutions also. 5 and 6 are the least positive solutions. Now, between Krishna Devigna and Bhaskara too, they have analyzed the Kuttaka equation in several ways. I am going to show some of them. Kshepa abhave hatva yatra kshepa shuddhyet harodritah Nyeh shunyam gunah tatra kshepo haragritah palam. The equation is, now here Shepa, the constant term, should be made 0. So 17x plus 0 equals 15y, or 17x equals 15y. Therefore x by y is equal to 15 by 17. That is one solution. Or x is equal to y is equal to 0. Or 17t equal to 15, t takes the value 0 plus or minus 1 plus or minus 2 up to infinity. Second, the equation is of the form 17x plus 1 equal to 15y. This has got the name Kuttaka and it's used mainly in astronomy. Valli is as below 1, 7, and instead of 5 we have here 1 now, followed by a 0, and you get the two solutions 7 and 8. X is equal to 7 and y is equal to 8. So 17 into 7 plus 1 equals to 15. From this equation, you can find out, instead of 1, if you put any other number, all the three have to be multiplied by the same number, and you can get the solution for any equation. From this we can solve 17x plus 5 equals to 15y. That is 17. Original solution was 7, so multiply by 5. Original solution was 8, multiply by 5. It's the same as above. Yogaje takshanat shuddhe गुणाप्तिस्थो वियोगजे धनबाजो भवे तद्वत् भवेताम ऋणबाजयोः. Now you know that 17x plus 1 can 15y can be solved. Then 17x minus 1 is equal to 15y can be solved easily. It's called the reverse solution. Now here you have 17 into 7 plus 1 equals 15 into 8. Then according to the sutra, so 17 into this 15 minus this solution 7 minus 1 equals 15. Take this coefficient 17, subtract the 8 and you get 136 minus 1 equals 135. That solution is 8, 9. So for any number you can do this. You get the, sometimes only the minus solution is available. So from that you can go to the plus. Or if the plus solution is available, you can go to the minus. The difference between the coefficients is 1. Now if this equation is like this, 17x plus 1 equals to 16y. Now this difference, 17 and 16, they have a difference of 1. This can be solved by putting x equal to 1 and y is equal to... You change the equation to a minus solution, just now I told you. Then you have 1, 1 is a solution. 17 into 1 minus 1 equals 16 into 1. Now reversing 17, coefficient of y minus 1 plus 1, 16, coefficient of x minus 1. That is 17 into 15 plus 1 equal to 16 into 16. That is 15, 16 is a solution for the equation. Difference between the coefficients equals kshepa. Now, here let us have an equation like this. 17x plus 2 equals 15y. 17 minus 15 equals 2. Now what do you do? First solve this equation where we get x equal to 1, y is equal to... See, sometimes the author says, just by looking at it you should know the answer. So it is obvious that 17 minus 15... Then just looking at it, if you put x equal to 1 and y is equal to 1, you get the equation x, 1, 1, it's a solution set. Then you have to do the reverse. 17, 15 minus 1 plus 2, 15, 17 minus 1. That is solution set is 14, 16. இவ்வளோ பெருசாக எடுத்தது அடுத்து அதான் இல்லை இதான் 5 இது பண்ணிட்டேன் அடுத்தது பண்ணேன். Okay. Now kshepa and one coefficient have a common factor. So 17x plus 5 equals 15. Right? Now 5 and 15 have a common factor 5. So you divide the equation by 5. 17x plus 1 equals 3y dashed. Now y has become y dashed. Now this is also drishya. When you look at it, you know that 18 is equal to 6 times 3. So you can write obvious that 1, 6 is a solution set. So multiplying 17, 1 and 3 by the common factor 5, we have 17 into 5 plus 5 equal to 15 into 6, or 5, 6 is a solution set. Difference between the coefficients, that is a factor of the kshepa. Now this is 21 and this is 17, difference is 4 and that is a factor of 16. So you can write it as 21 into 4 minus 4 times 4 equals 17 into 4, that's obvious. All of them have 7 as common, 21 minus 7 minus 4 equal to 17. Now for 21 into 4 minus 4 comma 0 is 17 4. Solution set is 4 comma 4. Hence now you have to use the reverse. You have to do the reverse. 21 into 17 minus 4. You put the plus sign. Now it has gone from negative to positive. So you use the reverse formula. Is equal to 17 into 21 minus 4 or 21 into 13 plus 16 equals 17 into 17. That is 13 comma 17 is a solution set. Now you have a problem here. 21x plus 15 equal to 13y. Of course, after analyzing all the methods, finally when you have a problem, you choose one of the methods. I can choose the method that this and this have 3 common, and if I reduce it and do the problem. But I am going to show you another method, where by successive division we have here, after the second division you have 5 as the remainder. 5 is the factor of 15. So you stop the valley there. You take the two quotients. I am taking the 2 quotients, and my Kshepa is here, and I followed by 0, and I form the valley 6 and 3. So x is equal to 3, y is equal to 6 is the solution. 23 into 3 plus 15 equal to 13 into 6. Solution set is 6 comma 6. So you have minimized the steps, that's all. When you find it comes to this after the second division, you stop it there and proceed as before. Negative divisor. Let the equation be 18x plus 10 equals to minus 11y. You do the successive division and write the valley 1, 1, 1, 1, then you get the. Therefore, x is equal to 30 minus 11 by 2 is equal to 8, and y is equal to 15 minus 18 into 2 equal to 14. 18 into 8 plus 10 equal to 11 into 14. That is 8, 14 is a solution set. Obviously, the solution set for 18x plus 10 equal to minus 11y would be minus 14. That is all the difference. Because only then you can get a positive here. So, if this minus, answer should also, y should be minus. Then you will get 18x plus 10 equals minus 154. Again for the equation 18x minus 10 equals to minus 11y, it would be minus 8 and 14, that's all. There's no difference in that. Negative dividend, we should take the same equation. Minus 18x plus 10 equals 11y and minus 18x minus 10 equals 11y. Taking y to be positive, solution set for the A would be minus 8, 14, we have just done before. And for B, the solution set would be 8 minus 14, since both 8 and 10 are negative. Samslishta Kuttaka. This is another variation given by Bhaskara. It is of the form that take 2 equations and solve them together. 63x plus 7 equals 5y and 63x plus 14 equals 10y. What you do is you have to add these 2. This is common for both. Add these 2 and add these 2. 63x plus 21 equals 15y. Dividing by 3, you get 21x plus 7 equals 5y. Since 7 is a factor of 21, the equation can be rewritten as 3x plus 1 equals to 5y. Where x is equal to 3, y is equal to y dash equal to 2 is one solution. Now if you put x equal to 3, add 1, it is 10. That's equal to 5 into 2. So this is a solution. X equal to 3, y dash equal to 2 is one solution. Therefore, x equal to 3, y is equal to 2 into 7, because you divided it by 7 earlier. is equal to 14 is a solution for, that is 21x plus 7 equals 5y, that is 21 into 3 plus 7 equal to 5 into 14. So this is called Samslishta Kuttaka, where you have two simultaneous equations with dividend same, only the kshepa and the divisors are changing. Odd quotients. Now what happens if there are odd quotients and even quotients is also discussed by Krishna and Bhaskara too. Consider the equation 60x plus 3 equals 13y. You have the, after successive division, you have the quotients 4, 1, 1, 1, 1. Kshepa is 1. Kshepa is 1. It should be 3 actually. And then you have the quotient 69, 15, 9, 6 and 3. Y is equal to 69 minus 60 equal to 9. X equal to 17 minus 13 equal to 2. Now without reduction for odd number of quotients, as per the sutra, the top entries in the valley do not give the solution. For 60 into 2 plus 3 is not equal to 13 into 9. On the other hand, if reduction is again you reduce, then as necessary, then y is equal to 11, x is equal to 15 is the solution. So when all the Bhagyahara and Kshepa are positive and all the quotients are odd, the second reduction is essential. No, what it actually means is it should work so that you get a solution. A little bit of manipulation, but nothing is against arithmetic or algebra. But you have to think, oh, I'm not getting a solution here, let me go to the other method. Now, this is very useful when you have a large number in the as constant term. I have not taken that, but I have taken a smaller example. 5x plus 19 equal to 3y. Now what you do is reduce the equation with 3, which is the divisor. So 5x will become 5 minus 3x and 19 will become 19 minus 18. That is, you are dividing by either 3 or a multiple of 3. Either 3 itself or a multiple of 3. So you get the equation 2x plus 1 equal to 3y. Again you have Drishya, you look at it, you know the solution, first solution. X is equal to 1, y is equal to 1. It's obvious that this is the x is equal to 1, y is equal to 1. Now for the original equation, 5x plus 19 equal to 3y, x will be the same 1, but now y is equal to 24. This 5y has become 3y has become 24, so y is equal to 8. So when you have very big numbers here, to divide by the divisor and reduce it to remainder, it will be usually less than these two. The remainder will be small. So you can work the problem, then go back to the original equation. Even quotient, we did odd quotient.
Somebody is having a doubt.
I have a, see, these are the equations, the previous one. You can, when you assume x equal to 1, you just have to subtract on the right hand side, right? And you get y.
Please come and tell.
Can you just go to the previous one? Here, when the equation is 5x plus 19, if I take x as 1, even have an issue. Morally and Adutena, after 3y is 19
I tell you, after learning all the methods, it is left to you to choose whichever method you are comfortable with or whichever method is easy. Just giving all the varieties of problems that you can come across. After some time, you won't know which one to choose because you have known all that. I should have added these two, I got 23, 24. So x equal to 1, y is equal to 8. No, there itself I got the answer. I didn't do that method. I reduced the constant term to the remainder and I done the problem. So, even quotient, consider the equation, earlier equation, 18x plus 10 equal to minus 11 by. So, Valli is there. After reduction, the solutions are 14, minus 8. But 18 into minus 8 plus 10 is not equal to 11 into 14. On the other hand, a further reduction would mean that y is equal to 18 minus 14, which is equal to 4, and x is equal to minus of 11 minus 8, which is minus 3, would be a solution. So for even quotients, second reduction is necessary. This is an example I have taken from a Tamil text which Dr. Rama also mentioned, Asthana Kolakalam. A tradesman died leaving a heap of pearls for his 7 heirs. Initially, 2 sons wanted to divide it between themselves. There was 1 remaining. Similarly, 3, 4, 5 and 6 sons tried to divide it among themselves. Each time one was remaining. But there was no remainder when the 7 sons divided it among themselves. How many pearls were there in all? This is the problem. So I found that it could be solved by using Kuttaka. I don't know whether the author of Asthana Kolakanu was aware of this, but I was aware of it. I thought to solve it with Kuttaka. At first, the LCM of 2, 3, 4, 5 and 6 is found, and it is 60. The required answer should be a number which is a multiple of 60 added to 1, and the whole should be divisible by 7. So the equation is like this: 60x plus 1 equals 7y. The Valli is formed as follows. I got this as y and this as x. So, and I have done the reduction because of the odd quotient. So y is equal to 43, x is equal to 5. So number of pearls is equal to 7 into 43 or 60 into 5 plus 1. Either this side or this side you can take. So the least of such numbers, because it's going to have infinite solution, and for the tradesman, I am giving him benefit of the doubt. He had only the minimum of pearls. So
has all the other solution.
He just gives the answer. I only worked out, sir. He said Muttukal and then he'll give the answer. The least of such numbers is 301. Anything else will be more than 301, so I have taken the least solution. Example from astronomy. I told you the Samslishta Kuttaka, Stira Kuttaka is used for astronomy by the ancient mathematicians. The Ahargana or the elapsed days from the epocha. Sir, epoch, sir? Ahargana is the number of days.
Number of days elapsed from any epoch.
Multiplied by the number of sidereal revolutions of the planet and divided by the number of civil days in a kalpa gives the position of the planet, that is the number of revolutions up to the day concerned, both integral and fractional. The fractional would consist of, after days we will have number of days, then you will have the number of revolutions. Everything will be in fractions, minutes, seconds, and then bhaga, degrees, and then so you will get the answer. In the example, revolutions of the planet is imagined to be 9. Civil days, Kudinani is 19 and Ahargana is 13. Now, Ahargana is given as 13. Now we are going to work it out so that you get Ahargana. Kalpyata Shuddhihi Vikalavasesham Tashtista Bhajyaha Kudinani Hara. Is given Tashtista Bhajyaha Kudinani is Hara. Tajjam Palam Syuhu Vikala Gunastu Liktagramatacha Kala Lavagram. Let the remainder of seconds, after seconds, it's further there is remainder, little bit, that is called the Shesham or the remainder. Remainder of session be the negative Kshepa. 60 the dividend, because you have to go to the next minutes. From seconds you have to go to the minutes. The quotient arrived will be the seconds. The multiplier will be the remainder of minutes. From this the minutes, the remainder of degrees and so on can be found. So the first equation is 60x minus 11 equals 19y. The second equation is also 60x because you are going to the minutes. 60x minus 11 equals 19y. 11 you got the remainder of the previous problem, now you are putting it here. Kuttaka is again done with Kalasesha. Here again the equation will be 60x minus 10 equal to 19y. See, this 19 will be constant, but this and this will change. By Kuttaka, the least solution set is 1650. Then Labdhi is 50 Kala minutes and Guna 16 Bhagasesha, remainder of degrees. Now you go to degrees, 30 degrees. So you go next equation is 30x minus 16 equals 19y. Kuttaka has again performed Rashi Sesha. How many Rashis? 12. So you have 12x minus 17 equals to 19y. By Kuttaka, then you again Bhagana Sesha. Kuttaka again is finished Bhagana Sesha. Here the equation is 9x minus 3 equal to 19y. By Kuttaka, the least solution set is 1360. Labdhi is Gata Bhagana, the past Bhagana, and 13 is the Haragana. So you assume there is a power cut, we are using the generator. So we assume that the equation that Ahargana is 13. So we work backwards and got the answer as Ahargana. 13 equal to Ahargana. Now Yukti Bhasha. Yukti Bhasha is a text by Jeshtadeva, one of the Kerala mathematicians. I've just taken one example from his text. If for the civil days, and he lays importance on the rule of 3 or proportion. If for the civil days of Yuga, this much is the number of Bhaganas, revolutions of the planet, then for the currently elapsed civil days, what is the Bhagana? So obviously a case for ratio or proportion. Thus the number of completed Bhaganas is got. Then from the remainder, Sesha, the segment of the revolution in terms of signs, Rashi, what we did earlier, degrees, Bhaga, minutes, Kala, and Bikala is seconds, can be got by multiplying the remainder respectively by 12, 30 and 60, which is what we did for the earlier problem. While solving Jeshtadeva, while solving it almost is as if he is taking the example from Leelavati and Bijaganitam. While solving linear equation, the terms Apavartana reducing to the lowest term, Valli putting the creeper, Valli Upasamhara working the creeper are explained. It is to be noted, very important, that in Yukti Bhasha Katapayadi Sankhya is used. Katapayadi expression, Madam explained, according to the alphabet. And whereas in Bija Ganita, Bhuta Sankhya is used. Bhuta Sankhya with some number is denoted by something. It's like that. The Kuttakara process, he calls it Kuttakara. Process itself is given in the 4 verses which occur in the Leelavati and Bijaganita. The example cited by Jeshtadeva is also the same as in Leelavati to solve for integral solutions of the x and y in the equation 221x plus 65 equal to 195. Same example is used and he's explained the method also. This is an example of Sthira Kuttaka. The number of revolutions are 570. The Tatsama, what I have written in the bracket is the Katapayadi. Tatsama. And the number of civil days in Yuga 210389. The Jagannupura. These are reduced Apavartita quantities. The Kshepa is to be taken as -1. So consider the equation 576x minus 1 equal to 210389y. To find integral solutions for x and y, we are going to do the mutual division. The big number. So you have a long, but it comes to 1. So you stop here and take the quotients. So this is the quotient 365, 316, 2410. So 94602 Ratna Stambharda and 259 Dharmarat 67, 58, 94. So x is equal to 94602 and y is equal to 259. Therefore, 576 into 94602 minus 1 equals to 210389 within bracket 259. As explained earlier, it's easy to find the solution of for plus 1 by doing the reverse process. So 576 into 210389 minus 94602 plus 1 equals 210389. 576 minus 259, that is 576 into 115787 plus 1 equals 210389 within bracket 317. That is x is equal to 115387, y is equal to 317. The Kuttaka equation or the method was considered important by almost all Indian mathematicians. It helps in solving the topic I am going to deal with in the afternoon, Varga Prakriti. It starts with Kuttaka. It was used in astronomy for finding the position of the planet and so on, is what we did. It was also used in solving some equations of several unknown, which Bhaskara deals with in his Bijaganitham. Thank you. சொன்னேன் இப்போ
Thank you very much, ma'am, for introducing us to the aspects of algebra in ancient Indian mathematics.